Right, welcome. This is question 5 for AQA AS Physics video for June 2013. Now, for question 5, we're given this, well, it's not very accurately drawn anyway, but I've given the key bits of information that you need, as always. You're welcome. Basically, we've got this alternating current here, and we're being shown the difference in voltages. Now, obviously, it's not one out your plug because so you've got 62 either side, and we're given the time sensitivity in milliseconds. So we've got 2 milliseconds, 4 milliseconds, 6. Now, I put 5 here where it goes through. It doesn't tell you it's 5, but obviously it's clear because it goes halfway through between 4 and 6. And you have to be a genius at maths to realize that 5. That is 5. But a key thing to know is the distance between each. Sorry, just popular guy. You've got 10 little squares between 2, and every 2 you've got 10 little squares. So every 10 you've got 2. So every 2 you've got 10 little squares. So obviously, if you denote that down, therefore you've got 5 little squares, or 1 big square for a change of 1. So therefore, each little square represents 0.2, or 0.2 milliseconds, or whatever you want to think of it as. Now, that's not relevant for the first part. The first part says, state the peak-to-peak voltage. Now, it's very easy to put plus 62 to negative 62. That's a peak-to-peak. Now, it's actually asking, in an essence, it's asking the difference. Sorry, I think that's, 62. Sorry, 64. I do apologise. I've just drawn, now it doesn't tell you it's 64, but if you work out 60, then each little block is each little block, it counts as 4 if you work it out, and then obviously that gets you your 64, negative 64, not 62. So your peak to peak is the distance between them. Distance between them is obviously 64 times 2, or 64 take away negative 64, 64 plus 64. So therefore the peak to peak voltage is 128 volts. Okay, so that's how they come up with that figure. So A part 2. A part 2 says state the peak voltage. Now that's just either one of them two. So you can either put positive 64 or negative 64. So it's totally up to you which way round you look at it. Let me see what the mark scheme says. If mark scheme says plus 64, so I'm not sure you get away with saying negative 64, but just to be safe, I would leave it as positive 64. Now, question part 3. So question part 3 says, A part 3, calculate the root mean square value of the alternating current. So either you know this or you don't. Now, the root mean square value, to say essentially what that means, although it has no actual bearing on how you answer this question, it's just one method. It's the value of the alternating current that you would have to use to get the same value as using a direct current through a fixed resistor. I'm showing there's some other bits, but anyway, you're not really needing to understand that for this question. The best way of looking at this question, I probably didn't say the right definition, so I almost shot myself in the foot kind of thing. I need to have another look at that, but let's hope that comes up as a question. Anyway, the root mean square value. Now, root mean square value. The only way of explaining this is basically, this is the formula for coming up with the root mean square of something. So, we've got the peak. So, generally we'll do the voltage. So, if we do the voltage, so it's the peak voltage, or peak V, over root 2 is equal to the root mean square value. Now obviously you can tell, therefore, because root 2 is 1.1 something, that obviously the root mean square value is always going to be less than the peak value. That's just a kind of formula you need to get to grips with. As I said, the official definition for root mean square values, I think is pretty much what I just said. When you get a value for the alternating current that would give the same value as a direct current through a resistor, and then you add on something about power, something about power. I do apologise, I haven't looked at root mean square for quite a while. So basically, that little explanation, as crude as it was, gives most of the explanation for the root mean square value. Probably should end up redoing this video just to make myself look like, not look like a complete idiot. But anyway, as I said, that explanation, or the official explanation, the proper definition, has no bearing on this actual equation. Well, obviously it does, but for you and I doing AS Physics, it has no bearing on that. We can't see any resemblance straight away. That's just a formula you need to be able to understand. Now, the only two questions they will ask on root mean square value, one of them I clearly need to go and look at again, is what the root mean square value is, so in terms of defining it, and the other question will be to convert a peak voltage, in this case this exact question where it's asking us to convert a peak voltage into a root mean square value. So the alternating current, so that's why it's asked us to work out. Now, you could have worked out something to do with the peak voltage, because it's just asked you to work out the peak. So it's, anyway, so it's 64 volts over root 2, and if you put that in your calculator, you should get 45.3 volts as a root mean square value. Okay. So the next question, so that's A part 4, says calculate the frequency of the alternating current, state an appropriate unit. Now we need to do a bit of background to this. The first, well, it's the number of oscillations per second, that's what it is. But we can't go, okay, well this is milliseconds, and we'll find out over here somewhere, and we just extend the graph. You can't do that because, well, they would have done that for you. Wouldn't have been able to ask you to draw another part of the graph. So obviously we can't look how, because remember this is milliseconds, and we have to use standard SI units, so scientific instrument units, basically ones our physicists use, because that's what fits the equations, and they can't bother creating other ones for other equations because they're lazy. Obviously, you know, I could clearly. So the only thing we can do, therefore, is we need to work out, okay, well, what's the time period? Now, we've clearly got a time period here, but you've got to remember that we've got it in milliseconds, okay? So, so let's just remember what a millisecond is, a conversion from second to a millisecond. So, if you've got a second and you want to convert it to milliseconds, obviously milliseconds is going to be a lot greater because they're smaller. So if you were converting from milliseconds to seconds, you divide by 1,000. So milliseconds to seconds, you would either divide by 1,000 or times by 10 to the minus 3. But if you were going from seconds to milliseconds, obviously increasing, milliseconds to seconds, yeah, if you were going from seconds to milliseconds, then you would divide by 10 to the minus 3, or times by 1,000. Or you just remember one of the ways, but that's just essentially saying the same thing. So you times by 10 to the minus 3 when you're going from milliseconds to seconds, because you're making it smaller, and you divide it by 10 to the 3 when you go from seconds to milliseconds. Okay, so now we need to go back to looking at our good old friend, the graph, to see what the time period is. Now the time period, remember, is, this is just like looking at a sinusoidal wave. So basically, it starts here, if we imagine this is the start of the time period, it's not going to be at 5, because that's only one loop, essentially we've got to go up and then back down and up again. So if we follow it, we hit 10 seconds. So therefore, and remember that, sorry, it's not 10 seconds, it's 10 milliseconds. So the time period is 10 milliseconds. However, that is not in seconds, so we can either follow one of the two routes there. Doesn't matter which way you do, as I said, you get the same answer, so it's 0.1 seconds. Just make sure that's right, I'm not going completely insane. So I've just making sure I've got this answer right. You know that I don't trust myself, but I just want to see what they've done. Okay, yeah. Oh, sorry, 0.01. So I did that off the top of my head, so I do apologise. 0.01 seconds. So therefore, as we know, we don't want the time period, we want the frequency, but we know one over the time period is a frequency, so it's 1 over 0.01. So therefore, the frequency is 100 Hertz. Okay? So let's remember frequency is the number of cycles per second. So if you would continue this on, then you would get 100 of these going up and down until you reached a second. Okay, so the next part B is quite a tricky one to understand, but especially just from looking at the mark scheme, I do think it's a little bit of a nasty one. So it says on figure 2, so that's our basically our drawing of this, well, not our drawing, it's on the example, that's mine, of this sort of alternating current, and we are asked to draw a line that shows the same direct current voltage that gives the same energy dissipation in R as produced by an alternating wave form. Now, what that essentially says is that says the root mean square value, okay? So, actually I'm quite glad that question came up because it allows me to explain what the root mean square value is. So that's another way of saying, now, what it says is the same, so the value of the direct current that gives the same energy dissipation as R as produced by the alternating waveform. That's just the alternating current. So basically, rephrase it, what question B actually says, draw a line to show that show the DC voltage. So basically, a value of the voltage on this graph that will give the same energy as dissipated in R by the alternating current. So that's the other little bit. Sorry, I missed off the root mean square value definition. Okay, to give the same power, R, remember, is a resistor, so I was right when I was talking about resistors. I just missed off the power bit, so I do apologise about that. So the root mean square value is pretty much what it says in the statement for B. Now you've calculated the root mean square value of 45.3, so it looks something like this. Obviously yours would be a lot straighter than mine. Now if you look on the mark scheme, the mark scheme says horizontal line, so obviously you've got to get that, there's 2 marks here, and you get the other mark for doing it through y equals 45 brackets 44 take 48 brackets x. What does that mean? Well, I'll tell you what that means. Basically, obviously you've got a margin for error, because not everyone is going to be able to do it bang on, because that's 45.3, so some people might do it up, some people might do it down, but it's this essence really of just little margins for error. Basically, it just says y equals 45x, so basically what it's saying is y is a straight line through 45. Okay, and they allow a variation from 44 to 48, so if you've got drew your line inside 48 to 44, then you get the mark. If you draw it outside that, you don't get the mark, even if you draw a horizontal line, because you might just assume, okay, well, you might just not know what he was talking about and just assume, oh, it gives the same, what's the direct current average of this, and drawing it at 0. So obviously that'd be wrong, because that's a classic mistake that most students made. Okay, so hopefully that's helped in part B. So part C says an oscilloscope has a screen of 8 vertical lines and 10 horizontal divisions. Describe how you use an oscilloscope to display the alternating waveform in figure 2, that so 2 complete cycles are visible. Okay, so we know basically what I'm saying is what do we need the bottom division to be. So obviously we need to alternate the y-axis and alternate the x-axis. Sorry, I was just freaking out because there's a lot of grapes going on. So we know the time period is 10 milliseconds. So obviously if we want 2 time periods, then it's obviously going to be 20 milliseconds. So we need each division to be 20 milliseconds. Obviously you need to adjust the time base. You don't need to say y or what byte. You need to say we need to connect to the y input and adjust the time base. Okay. Alright, so hopefully that's helped. So that's question 5 over and done with. As I said, I will have another go at that, but I'm assuming that is helpful. Alright, so thanks for watching, and we'll see you in the next question.